Welcome back, students. Let us now discuss histograms, section 2.2 of our textbook. Let's begin with an example. And here's an example of a standard histogram coming from the same data set that we had been dealing with. We use the same data set for stem and leaf display, dot plots, and actually everything. Pie chart, bar chart, Pareto diagram, the same thing, to tell the truth. Part of the reason I wanted to do some comparison. Anyway, here it is. With the same data set, score distribution of 33, 58, 64, all the way up to 94, and we have this kind of histogram. Here's another standard histogram. What's the difference between these two? The latter seems a little bit fatter, and the third standard histogram. This time the rectangles are thinner. And what do they mean? That's one of the several questions that you have to ask yourself. And here's another. What is the fundamental difference between the histogram and the bar chart? I said fundamental difference. Not a minor difference like, whoa, here is a gap between these boxes. Well, that's just minor point. That doesn't really count. The fundamental difference, well, actually, it's here. Let's go directly to a conclusion. In a standard histogram, width of each rectangle corresponds to something called class interval. And height corresponds to frequency or relative frequency. Now, what is the class interval? Class interval is something like this, a certain number to another number. Here, I set the class interval size uniformly as 10. So 90 to 100, there's one class, actually a class, and there's one student who made that, so frequency is 1. So we have height 1 in this box, all the way to the right hand side. Next, we have 80 to 90, and there are 6 students. And that is the frequency. So what do we have here? Width is 10, height is 6. Now let's go to C class. Between 70 to 80, there are 10 students. So width of this rectangle is 10, height is also 10. Now D class, between 60 to 70, width is again 10, uniformly 10. The height is the frequency, 4. And the next class between 50 to 60, there's 1. The next class between 40 to 50, 0. And finally, the lowest class between 30 to 40, there's 1. So we have these kind of rectangles. Again, let me emphasize, width of this rectangle corresponds to class interval width. Height, in this case, frequency. You could use relative frequency too. All you have to do is divide everything by 23, the total. And instead of 10, you're going to get 10/23. Instead of 6, you're going to get 6/23, which will be all the decimals. And you can convert those into percentages and so on. But will that change the shape of these rectangles? No, they won't, because it's just vertical scaling. So the rectangles will remain exactly the same, and only the labeling of the vertical coordinate axis will change. Instead of 10, you're going to get 10/23, which is what? 0.434 something will be the height of the tallest rectangle, and so on and so forth, if you change everything to relative frequency. Frequency, relative frequency, they make absolutely no difference here. That's just vertical scaling. Width, on the other hand, is very, very, very important. Width of each rectangle corresponds to class interval. Now, what if I change the class interval size into, say, 15? Well, that's what we are looking at over here. Between 85 and 100, how many students are there? There are 4. So this box, the right-hand side, has width 15 and height 4. Next class, between 70 to 85, there should be 13 students. And yes, width is 15, height is 13, and so on and so forth. So we are dealing with the same data set, but different class interval widths. Consequently, we have a little bit different histograms. Third picture, this one is given by class interval width of 5. Between 95 and 100, 0. Between 90 and 95, 1, and so on and so forth. How do we create standard histograms out of scratch? Typical method is to create frequency table. Here's an example of a frequency table. Form a table and then get all the class intervals between 30 and 40, 40 and 50, 50 and 60, and so on. But we have to be precise. So in this case, greater than or equal to 30 and strictly less than 40, greater than or equal to 40, strictly less than 50, and so on and so forth. We get all these class intervals and count how many items are there, how many entries are there in each class interval to get frequency. We get 1, 0, 1, 4, 10, 6, and 1 respectively, and those are going to be the height of all those rectangles. Or you can divide everything by 23, the total, and get these decimals, or in terms of percentages, you're going to get 4.34783, so 4.35%, and then 0%, 4.35%, and 17.39%, and so on and so forth. And those are going to be the heights of all those rectangles if you use relative frequencies. But then again, as I said early on, that makes no difference in terms of shape of those rectangles. What if you want to change the class interval width? Instead of taking 90 to 100, you start from 85 to 90, and then this one will be 70 to 85. You may call it kind of generous curving or something. A students will be 80 to 85 to 90, and B students will be 70 to 85, kind of like that. Very generous curving. That kind of thing is called standard histograms. Let's see, do we have enough examples for, do we have enough time for an example? Okay, let's go over to an example here. And the following table shows the monthly electricity usage of a certain household, mine to tell the truth, from, well, June 2013 to June 2014, and produce a histogram. And archive, we are going to talk about archive in a separate video, so histogram only. Now you're free to take any class interval, and I happen to select 250 kilowatt hours as class interval. Why? Because, as a matter of fact, this came with my electricity bill. And as you can see, this graph you're looking at, your electricity usage, June 2013, July, August, September, and so on and so forth. This one is a bar graph. This is not a histogram. Why not? Well, if you point toward a minor difference that these boxes are not touching each other, you don't get any credit. 0 credit from that kind of answer, no. What is the fundamental difference between histogram and bar chart? The width has to be class interval, and height has to be frequency. In this case, neither. Width has no meaning actually in this case. January, February, March, those are just nominal variables. And that height is not really frequency either, it's just electricity usage. But it does give me good candidates of, what do you call this, class interval, because if you look at the vertical axis, they're kind of divided into 250, 500, 750, 1000, 1250, and so on. The generic class intervals are kind of given here, so let me use that. So how many months are there between, say, 1250 and 1500? I see 3, July, December, and January. Those 3 months have boxes ending between 1250 and 1500. How about between 1000 and 1250? There are 2 months, June 2013 and February 2014. Oh, 3, excuse me, June 2014 as well. There are 3 of them. And so on. You can actually count those. Of course, you can count everything from this table as well. Anyway, here it is. Here is the class interval and frequency. Between 500 and 750, there are 4 such months. Between 750 and 1000, 1 such month, and so on and so forth. And here is the histogram. Class interval size is 250, and we have 500 and 750, and 750 to 1000, 1000 to 1250, and so on and so forth. And height of each rectangle is the frequency, 41332. And of course, if I select different class interval size, then I'm gonna get different histogram. For example, let's change this to 200. And of course, we have different histogram, kind of like this. Of course, if I do that, I have to completely redo this frequency table. So the class interval goes from say 500 to 700, 700 to 900, and so on and so forth. By the way, you see there's a gap between 700 and 900 according to this new histogram. That's because the frequency there is 0. So rectangles touching each other is not absolute trait for histogram. Really, absolute trait, absolute characteristic of a histogram is class intervals for horizontal and frequency for vertical. You can use relative frequency too by dividing everything by the total number and getting the decimal or percentage. Will that change the shape of the histogram for how many times I cannot count? No, no change whatsoever, because that's just vertical scaling. Only you can change the labeling of the vertical axis. Oh, by the way, here is a wrong solution. As a matter of fact, I gave this problem in my 1580 class number of years ago, actually about that time. And it turned out almost everybody produced graph like this and consequently ended up with 0 credit. This is not a histogram. This is just a bar graph. Bars are touching each other. That does not mean it's a histogram because it is not a fundamental characteristic. It is really a minor point. What is the fundamental characteristic of a histogram? I don't know how many times I repeat it, but here we go again. Width has to be class interval, height has to be frequency or relative frequency. And depending upon the kind of class intervals I have, histograms bars may not touch each other all the time too. So just relying upon boxes touching each other is a bad idea. This is wrong. This is not a histogram. Boxes are touching each other, but look at horizontal and vertical labeling. No, no, no. And this is right. And that's related to this kind of frequency table. Creating a frequency table is a necessity if you use paper and pencil method. But if you use technology aid, like the way I did, like Mathematica, then you can create histogram a lot more efficiently. There's a way to produce histogram with Excel too, and I'm going to talk about it in a separate video, as an optional video, of course. It's a little bit complicated. In the next video, I'm going to talk about advanced histograms. Looks like I have a little bit of time to talk about types of histograms, so let's go. Here are some types of histograms: symmetric, and then let's see, third one is called skewed to the right. You can see the histograms that stretch to the right. And then the fourth one is stretched to the left, called skewed to the left. And the final one is called bimodal. As a matter of fact, mode means the peak. And if you look at the first histogram, it has only one peak, so it's unimodal. The sixth one, it has two peaks, so it's bimodal. Those kind of things are characteristic traits of some histograms. through which we classify them.